Today we will begin with proof of the correspondence between Kalodjera-Moser, rational Kalodjera-Moser system and Kadamtsev-Petviashvili equation on the level of hierarchies. This means that in Kalodjera-Moser system we have Hamiltonians where k is positive integer. Only n of them are independent, where n is number of particles, but in principle there is a whole series of them. And this is in Kalodjera-Moser. So we can speak about a hierarchy of Kalodjera-Moser systems with different Hamiltonian flows, and all of them are compatible between each other because Poisson brackets between them are zero. On the Kp side, we have time variables tk and integrable flows, which can be represented as vector fields, derivatives with respect to this tk. And we considered singular solutions of Kp equation with a finite number of poles, and we considered rational, trigonometric, and elliptic solutions. Now I will speak about rational solutions. So in rational solutions, the tau function as function of x, which can be identified with t1, t2, t3. This was y, and this was t in original consideration of Kp equation. And for rational solutions, this tau function is a polynomial in x with roots which depend on all the times. So these roots of tau function are actually poles of solutions to the Kp equation, because the solution is a second logarithmic derivative of this tau function. And we are interested in dynamics of these zeros when the higher times under evolution with respect to higher times. We proved that the dynamics with respect to T2 is precisely the Kalodjera-Moser, rational Kalodjera-Moser dynamics with the standard Kalodjera-Moser Hamiltonian, H2. And now we will try to prove a more general statement that the dependence of these roots in higher times, so the under flow tk for arbitrary k, is the same as the Kalodjera-Moser dynamics under the Hamiltonian flow hk. This result was first proved by Japanese mathematician Takahiro Shiota in 1994. And I will try to repeat his proof with some modifications. So this is not exactly what he suggested, but in my point of view, this proof is better than his. So our tau function is represented in this form, and the psi functions can be written in general in this form, where this notation psi is, we already introduced it, it is the generating function of times. And in rational solutions, this is can be expanded as a sum of simple pools with some residues Cj which may depend on z is spectral parameter, and all times t, but not on x. This is psi function, and we also need the adjoint psi function. With some other coefficients C star. And we will use the following identity, which we discussed last time, and it is a simple consequence of the general bilinear integral equation for the tau function, and it looks as follows. So there, the integral over some neighborhood of infinity and what we are going to do is to substitute these expressions into this identity. What do we get? Something like this. So both sides are rational functions of x. Here the coefficients depend on z. Are rational functions of x with poles at the points x, j. And the highest order pole is second order when we multiply this by this. And on the right hand side we have only the pure second order pole. So we should make equal coefficients at each second order pool, and in this way we obtain the following relation. Next, we should recall the derivation of dynamics of poles with respect to T2. Introduce vectors with components C1, Cn. So they are columns. I transpose this row vector. And C star. The same with star. Oh no, here C star is regarded as a row vector. It is dual to this. And our solution was that C is minus Z minus Lax matrix inverse acting to the vector E, which is whose components are all equal to 1. And the solution for C star was like this. So we substitute this into here. And obtain and rewrite this relation in the following form. So we should take a residue at infinity of the following function. So this is inverse, the matrix inverse to Zi minus L, and we should take Kj matrix element of it. And here J K prime element. We can represent it in matrix form, introducing matrices Ej, which is diagonal matrix with one at element Jj and zeros in all other places. And the matrix E, which is matrix whose all elements are ones. And then this can be written as follows. it is an easy exercise to check that these two are the same. When you rewrite this expression in matrix elements, you get this. Now let us recall that the Lax matrix and the diagonal matrix whose diagonal elements are coordinates satisfy the following commutation relation. From it, we can express the matrix E in terms of all other matrices. So we should write E equal to Lx minus XL plus I. And we are going to substitute this expression into here instead of this matrix E. And also let us notice that the matrix EJ is nothing else than partial derivative of the Lax matrix with respect to momentum Pj, because the momenta are on diagonal of the Lax matrix, and non-diagonal elements don't depend on momenta. And we plug this and this into here. In this way, I omit detailed calculation, and eventually you obtain the following expression. You obtain the following. But now let us notice that these two terms actually cancel each other. They are equal because of a cyclic property of the trace, and also taking into account that X and this matrix are diagonal. So you can what should you do? You rewrite it in cyclic order. So you start from this matrix and rewrite under the trace. You rewrite it preserving the cyclic order in this form. But because these two matrices are diagonal, you can interchange them and get exactly the same which is here. So they are cancelled. And we are left with this expression. Now we recall what we recall. We recall this and write it as follows. Taking into account this result, we write it as minus a derivative with respect to Pj of the residue now you expand this into a series in Z, take the power degree -1 to get the trace and obtain that this is, but this is our Hamiltonian, so this is can be written as dHm over dpg. So we obtained the first half of Hamiltonian equations for velocities of coordinates in the time Tm. So they have Hamiltonian form. This is the first half of Hamiltonian equations. So the second one, to obtain the second one is a little bit more difficult exercise. I will not give all details, just the idea. Тряпки не вижу. So we have the relation already derived it. Let us differentiate it with respect to T2, both sides. Then we get dot means derivative with respect to T2. From the analysis of the dynamics with respect to T2, we derived the following evolution equations for vectors C and C star. Where M is the Lax matrix for the Calogero-Moser system. I write it in this way because C star is a row vector, so the matrix acts to it from the right, acts to the left. And this matrix acts to the right, to the column, and this is to the left. So we rewrite this as follows. So let me we recall that Pj is 1/2 of xj dot, and then write for derivative of the momentum from here. Write it in the following way. in matrix elements. Now again, you rewrite it in matrix form using the matrices E and EJ. And notice that using the explicit form of the matrix M, you notice that this is nothing else than this commutator is the derivative of Lux matrix with respect to xj. So you rewrite it in the following form. And substitute here, instead of this commutator, you substitute this. And instead of matrix E, substitute this. And then you get a similar expression to this, but the derivatives now are not with respect to Pj, but with respect to Xj. And so you get, in this way, you get the second part of the Hamiltonian equations. So this completes the proof. Now, a few words about trigonometric and elliptic cases. In these cases, especially an elliptic case, the problem of identifying higher flows of Calogero-Moser system with flows in KP hierarchy is more complicated. And for elliptic case, this problem was solved just a few years ago, very recently. And I will not give any derivative of this, but just formulate the result. And the result has a more complicated form than in a rational case, where the Hamiltonians of Calogero-Moser system corresponding to KP flows were just traces of corresponding powers of Lux matrix. In trigonometric case, the result is formulated in a more complicated way. So again, we have KP flows Tm, and now they correspond to Hamiltonian flows with Hamiltonian given by the following expression in Calogero-Moser system. I remind you that gamma is the inverse period. So it entered the potential, pairwise potential in this way. So I pi over gamma is period. And this gamma enters this expression. L is the Lax matrix of trigonometric Calogero-Moser. So you see that now this Hamiltonian is a linear combination of Hamiltonians given by traces of powers. So you m plus 1 degree cancels, but it starts from L to the m and all lower degrees, some linear combination. When gamma tends to 0, we get the result for the rational case, the previous result. You can try to derive this as an exercise, but this is maybe difficult exercise with star, so to speak. But nevertheless, you can try. And in elliptic case, the result is formulated in a not very explicit form. Consider the equation of the spectral curve, which is can be represented in the following form. Lambda is the spectral parameter which enters Lax pair, and Z is the second spectral parameter, and the equation of the spectral curve can be represented in this way. From this, you can define lambda as a function of Z. Just solve this equation with respect to lambda as a function of Z. And consider it as a generating series for some Hamiltonians. So this is the leading term. It's easy exercise to obtain this form of the leading term. And the rest is some series with coefficients Hn. And so this Hm are residues at infinity of that m times the function lambda of z. And the statement is that these Hamiltonians are Hamiltonians of the or higher Hamiltonians of the elliptic Calogero-Moser system, which correspond to flow in the time Tm, Kp flow in the time Tm. Okay. Now let me pass to another topic, to multi-component Kp hierarchy, from which, by considering its elliptic solutions, we will derive the dynamics of spin generalization of the Calogero-Moser model. So, what is multi-component Kp hierarchy? Now, the set of independent variables is larger. In Kp, it was T1, T2, T3, so on. In multi-component Kp, each Tk is itself a set of times. So now there are times they acquire additional index alpha, and now the set of times is so there are n if we have n component Kp, then alpha takes values from 1 to n. So we have n copies of this set numbered by alpha. And the Lax operator, which is pseudo-differential operator, it is still pseudo-differential operator in some variable x, which I will introduce in a minute. And this has a similar form as a series in inverse powers of differential operator. But now these coefficients are not numbers by n matrices. So when you multiply such pseudo-differential operators, you should take into account that coefficients don't commute. They should be multiplied like matrices. And so they are, each ui is a function of x and all times, all this set of times. And the dependence on x is introduced as follows. So x is added to all times with alpha equals 1. And all other times are without any x. So x is, you recall that in scalar case, the dependence of x was on T1 was just of this form. It was added to T1. And now the same x is added to all times with alpha equals 1. No, with the second index equals 1. And alpha runs from 1 to n. Here it is 1 and here it is n. We should also introduce, together with the Lux operator, pseudo-differential operators R alpha, which are series in the inverse power of differential, and the constant term is E alpha, where E alpha is the diagonal matrix whose only non-zero element equal to 1 is alpha alpha element. So the matrix elements are as follows. With some matrix coefficients, and these operators are required to satisfy the following commutation relations. So all of them commute with Lux matrix, and the product is like this, and also their sum over all alpha is required to be the identity matrix. And we impose the following Lux equations to these operators. It is convenient to introduce the so-called wave operator, which is a matrix pseudo-differential operator with the following matrix elements. With some coefficients which depend on x and all times. And then in terms of this W operator, the Lux operator can be obtained by the procedure which is called dressing, because we dress the pure differential operator with the help of this W operator. And also the operators R alpha are obtained by dressing of the matrix E alpha with the help of this W operator. Then, if you write them in this form, these relations become obvious. Because you see, the pure differential operator and the matrix E alpha just satisfy all of them, and you dress them from left and right with the help of W operator and get these relations. We can also introduce psi function, which is now is an n by n matrix. We act by this W operator to the exponential function. By definition, the inverse powers of differential operator act to exponent in this way. And the dual psi function is introduced by the left action of the W operator. Here it acts to the right, and here inverse operator acts to the left, where the left action of the operator dx, it acts to a function f at x to the left, is defined by in this way. So it's derivative of the function f with respect to x with the sign minus. It can be shown that these psi functions satisfy the following linear equations. So this A are differential matrix differential operators, and the psi star satisfies the conjugated equation. Where this operator A again acts to the left. Here it acts to the right, and here to the left. Okay, now the hierarchy which we are interested in is a sub-hierarchy of this, of the multi-component KP hierarchy. It is called matrix matrix KP hierarchy. And it can be embedded into the multi-component KP hierarchy by restricting possible values of independent variables of the independent times. In this way, each time t alpha k is put to be equal to some constant value, which is a constant, it doesn't change, plus a time tk, which is the same for all alpha. So in matrix KP hierarchy, the set of independent variables is the same as in KP hierarchy. It is just the set T1, T2, and so on. But the dependent variables are matrices. Then we can rewrite these equations just forgetting the index alpha. And AM now is L. It is just, so each A alpha M is L to the M R alpha plus, and AM, to obtain AM in matrix KP hierarchy, we should take a sum of A alpha M over all alpha. If you take the sum here, you have the sum of all R alpha, but because of that condition, it is just one, the identity matrix. So this is L, simply L to the M, positive part. In particular, we have, we need among all the infinite set of these linear equations, we need the first one with respect to the time t2, and it has the following form. And the conjugated equation is like this. Where V is the matrix which is minus derivative of the first coefficient in expansion of the function psi in inverse powers of z. So it takes has the form identity plus psi 1 over z plus psi 2 over z squared plus so on. And these are matrices, n by n matrices. And the this coefficient v is expressed as derivative of the first one. So since they are matrices, their order is important. Here we have v times psi, here psi star times v. We should conjugate not only differential operators, but matrices also. So the order is changed. Now we are going to consider elliptic solutions. When this v is an elliptic function. For elliptic solutions, we have that the matrix elements of this psi1 have the following form. It is some constant matrix S alpha beta plus linear combination of zeta functions with poles at xi. So there are n of them. With some residues r alpha beta. And it can be shown that in elliptic solutions to the matrix Kp equation, these matrices R alpha beta it also have index I, because they are different at each pole. That the rank of these matrices is 1. For solutions in general position. As such, they can be parameterized by two vectors with components A1, AN, and B, vector B with components B1, Bn. So they are columns. And then we rewrite this as so this V can be written as so now we are interested in dynamics in T2. And as you probably already see, that this will be coordinates of the particles of the Calogier-Moser system with spin, and these variables will be spin variables. But the derivation is a little bit more complicated than in one component case. Let me show some details. So as soon as the coefficient here in this equation is an elliptic function, we can find solutions among double Bloch functions. So for psi alpha beta, we can find it using the following ansatz. Again, we use the Lamé-Hermite function. But now we need both equations for psi and psi star. Where C and C star are some n-dimensional vectors, which and components of these vectors are these coefficients. So we should substitute this ansatz into this equation, and using this form of V here. So again, we have an elliptic in X. It is an elliptic. Let us put everything in the left-hand side. And the left-hand side is elliptic function of x with some poles. So we should make coefficients in front of these poles to be 0 to obtain the identity. And there are poles, the highest poles are of third order. And the condition that they cancel leads to the familiar condition that the scalar product of the vectors B and A belonging to the same particle is 1. This was our constraint. I recall that we omit the summation sign of sum when two Greek indices repeat. So this is a sum over mu from 1 to n. The next pole is second order pole. And here their cancellation lead to the equation, the following equation. eventually the cancellation of simple poles lead to the following relation. What should we do with this? It's not clear from the first glance. What should we do with this? How we shall resolve these conditions? And also, you should repeat this procedure for conjugated equation, for psi star, and obtain similar relation for which follow from cancellation of poles in the second linear equation for psi star, for this one. This step could be done also in scalar case, but there it is not necessary. The equations for psi is enough to derive the dynamics. But now, for spin case, it's not enough. We need to consider both equations. So let us introduce vectors C beta with components C1 beta, Cn beta. And C star alpha. Then those conditions can be written in the matrix form. And for conjugated system, we write them in this form. here this is a row vector, so matrix M acts to the left. Where L is the Lax matrix for spin Calogero-Moser system, and excuse me, here's another matrix, M star. Here's M, here is M star. And the matrix M has the following form. And M star where lambda I is the following expression. And lambda I star is a similar expression, but with B instead of A. One can prove that that actually lambda I is equal to lambda I star. I will omit a proof, it's not difficult. And then you can see that M matrix M is M star is minus M from here. So you obtain the compatibility of these linear systems gives the Lax equation. And we recognize here the Lax pair for spin Calogero-Moser system. And equations of motion which we obtain are written in the following form. for A and for B. These equations differ from what we had when considered the spin-Calogero-Moser system by these terms. They were absent, but in fact, it is easy to get rid of them just by noticing that the following transformation, AI alpha to AI alpha times some function Qi and Bi alpha to Bi alpha times the same function inverse. This transformation preserves the constraint that scalar product of these vectors is 1. And if we take Qi equal to exponent of the integral of this lambda I 2 times T2, then and rewrite this equation in terms of transformed vectors, you will see that this terms just comes. So we come to the equations of the spin Calogero-Moser system. Okay. Now this is probably all for today. Next time we'll consider a more general integrable hierarchy, which is called Toda lattice, two-dimensional Toda lattice. KP hierarchy is a sub-hierarchy of it. And by considering elliptic solutions to this Toda lattice, we will be able to reproduce equations of motion of the Rusinar's Schneider system.